So now let's start new section about martingales and some other tight concentration. So in many of our situations, we are interested in some random variable x, and we want to show that this is close to, say, some value, say m, meaning that the x minus m, okay, let's just write the expectation of x. We compute the expectation, and then we want to somehow show that the x being close to its expectation, say small, with high probability. So if we can show this, then we we know, I mean, with high probability, we know the value of this x, so which can give us more information about this random variable. So this, if we can show this phenomena is called concentration. And then if this is very small and with a high probability, then we might call it tight concentration. So this is what we want to show. But of course, I mean, this doesn't hold for every, random variable. It doesn't hold for all random variables. That's too much to hope for. So in many cases, x is some random variable. And this is not just any random variable, but it depends on other things. And in many cases, I mean, you can actually get this through certain process. So for example, let's consider x is the, number of heads in n coin toss. So you are flipping coin n times, and then coins are fair coin and which are independent. And after n time, you count the number of heads that you obtain, and that is your random variable x. If you want to compute this, how do you do it? You flip the first coin, and then if it's head, then you add 1. Otherwise, you don't add anything. You flip the second coin, you add 1 if it is head, and add 0 if it is tail. You keep do that. So throughout this process, you can compute the value of x. And this process can, the information on this process can be recorded in this way. And where xi is the number of heads in the first I coins. You are flipping coin n times, and each time you flip, you add 1 if it is head, otherwise it is 0. Then after first time you get x1, after second time you get x2, and so on. And the last moment you actually get the number x. So this value of x can be computed through this process with these intermediate values, which are also random variable. So our goal is to show that x is close to its expectation, say xn. More generally, we actually expect that every xi is also close to as we expected. So let's put it this way. So our expectation of x is n over 2. So let's say f of I is I over 2. Then we actually expect xi to be close to fi. So what we want to show is that the xi is never too far from fi with high probability. It's just a rephrase on the above. And in order to show that, so that's what we want. And in order to analyze this process, we have to also check the difference at each time. And then if we can somehow tell some information about the difference, how does it change, then we might be able to tell the final value. So if we want to show that this xi is close to fi with high probability for all I, then what conditions does this sequence of random variable has to satisfy? One of them is that the expected change, the difference must be, the expectation must be difference of these functions. And also one other thing is that we want this not too big. If every time so this not too big means that this is random variable. So this not too big means that the possible value that it can take and the possible value it can take, and then we consider the largest difference between them. Then we want to say this is not too big. So our intuition says that if we wish to prove that all of these xi are all close to fi, and then at the rest this is very close to fn, if we wish to show that, then obvious necessary condition that we need is, the expected changes must be changes of this function. And later we will get to this second condition also, but we also somehow want this to be not too big. So these two are the very natural condition to obtain tight concentration. So let's first focus on the first condition. And here we are dealing with this f. And in many of our situations, this f could be different function. And then it's not so convenient to carry over this f every time. So we just let x prime I be xi minus fi. Then if we know value of x prime I, then xi is automatically understood. So instead of xi, we might instead study about x prime I. Then in order to show that the xi is close to fi, we only have to show that the x prime I is close to 0 with probability large, some large probability close to 1. That's what we want to show. Then what does this condition become? For f prime, for x prime, that becomes that expectation of xi plus 1 prime minus xi prime is, if you plug this into here and with two different I, then what you get is expectation of x prime I plus 1 minus x prime I. plus, equals 0. Because you just move this to here and move this to here and then use the, these are just constant. These are just constant in terms of this. So these are not random variable. These are fixed number, which is determined only by I. So you just, put inside of this expectation, nothing changes, and this term and this term combine to here, and this term combine to here. So you get this. So we want to learn about, random variable satisfy this condition. That motivates the following definition of Martingale. So if we understand Martingale, then we can understand any random variable satisfy this condition for some function f. So, let us be able to deal with a random variable which can be obtained through a process, and while the process we have some expected behavior of this. So that motivates the following definition of Martingale. But here, actually, for the conventional reason, instead of this, we actually add this x0, which is the initial value, some constant value. Let's just assume that this is a random variable which always yields some constant. So actual process might start here. For this coin toss, this is 1 or 0, depending on the first coin toss was 1 or 0. But this is always 0 because we haven't tossed any coin, so the number of heads so far is 0. So instead of that, we consider, say, this, and then we want to show that the x prime I is very close to x0 instead of just 0. So now we define Martingale. Martingale is a sequence of random variable. Say x0, x1, xn, such that for every I and x0 to say xi, so let's consider these random variables are the ones that has value in real number. If you condition on the event, capital X and small x are a bit difficult to tell with my handwriting. Let's write it this way: x0, xi. So if you satisfy this, then then we call this a Martingale. So before I just wrote it this way, but I should have written it better way. So on my previous explanation, what we actually want is that when the xi, the process up until to xi is done, so process up until to xi is done, conditioning on that, if the changes next time is as expected, then we call it the Martingale. So this conditioning is actually natural. So what I explained here was not 100% rigorous, but that was the motivation of studying this Martingale. But if you think about it more, then this conditioning is actually quite natural. So conditioning up until to here, and then if we can measure the difference after that that process, then that leads to leads to how we can expect the random variables to be evolved in such a way. So, this condition might be just written in simpler way. So you just write the random variable here, but this is that for specific way of the process up until now. And if you condition on that, then the next one, in expectation, next one will be same as the current one. That means expected change from here. So up until to this process, assume certain process has occurred, and then conditioning on that, the expected change is 0 on the next step. So consider some example. So assume that a gambler with some money, with x0 amount of money, say x0 dollar, walks into a casino, and the gambler plays a fair game. The gambler flips a coin which comes up with head with probability half and tail with probability half. If this is head, then gambler earns $1. Otherwise, the gambler loses $1. Earns $1 with probability half and loses $1 with probability half in each round in each play of a game. Then, assuming x0 was some number and xi was some number, what's the expectation of xi plus 1? This is xi plus half times 1. With probability half you get, so let me write it this way. With probability half, your number becomes xi plus 1, and with probability half, your number becomes xi minus half. So this is same with xi. So this shows that this is a martingale. And we might change the game a bit. Now gambler actually bets an amount that the gambler wants. So the gambler can bet $2. In that case, if the coin is head, then the gambler earns the money, and otherwise lose the money, lose the $2 or earns the $2. Then the gambler actually can decide the amount of money the gambler bet. And even that can depending on the previous history. So for example, the gambler can do some strategy. Say strategy. Gambler decides to double the bet until he or she wins. So first time the gambler bets 1, and then if lose then 2, if lose then 4, and if lose then 8, and if lose then 16. And once he or she win, then stop and then starts from 1 again. So that's a one way of betting. But even with that, I mean, whatever that xi so far was. No, oh yeah, sorry. Oh yeah, previously this was 1. Then, I mean, that amount of money that he or she bets is say t. And t is actually a function, could be a function depending on the previous history. Then, or this t could be some arbitrary other random variable. It's not determined that. Whatever the t is, I mean, we have this inequality, so it is still Martingale. So that's some examples of Martingale. So, okay, maybe we need to see, I mean, also, I mean, some more examples of Martingale so that we can actually get used to it. So let's see what kinds of Martingale that we will deal with later in the next video. Let's consider some examples of Martingale.